And here it is. So hi everyone. So today it's a pleasure for me to host on this virtual seminar Michael Petersen, who is going to speak about a new picture for the Large Magellanic Cloud and the Milky Way interaction. So Mike defended his PhD at the University of Massachusetts in 2018. Then he moved to the Royal Observatory of Edinburgh in early 2019, where he stayed until this September or last September, when he decided to cross the English Channel to go to Paris to work at IEP. And because I think he was already tired of the Parisian life, he decided to go back to the Edinburgh University, where we will start with a new fellowship position. So Mike, if you want to start your presentation, thank you very much.
Excellent. Thank you. And thank you for the organization. Everything has gone very smoothly. Very happy with this. Very happy to be here speaking with you virtually about some of the research that I've been doing, largely research that I did that I've been doing in collaboration with people at the University of Edinburgh, although I have a variety of collaborators around. So Jorge Penarrubia is at the University of Edinburgh with me. Caitlin Donaldson's a student there. Sophia Lilla-Engen is a student at the University of Surrey, advised by Dennis Urkel, and then my thesis advisor, Martin Weinberg, and another student from Edinburgh, Ella Jones. And you'll see all of their names crop up during the presentation. All right, so the LMC usually needs no introduction, but I'll give you just a little bit to go off of here, what I think of when I think about the LMC. The LMC to me is, of course, the closest disk galaxy that we can see. It has an obvious bar, and as per my thesis, I would be remiss if I didn't mention that. Most of my thesis work was on dynamics of barred galaxies. You can also see hints of spiral arms in this Gaia DR2 promotional image, and you can tell that the galaxy is sort of obviously not in equilibrium. When we look at grand design spirals, you largely don't see this very apparent offset between the center of mass of the bar and the center of mass, as you would sort of infer by eye of the galaxy. Just to give you a sense of how I'll be sort of orienting myself through the talk, I largely like to think in galactic coordinates. So almost all of the images that you'll see throughout the talk will be oriented in this direction. So L is increasing to the left, galactic longitude L, and galactic latitude B will be increasing upwards. Also, if you were to zoom out significantly in this image, this promotional image from Gaia, you would see the small Magellanic Cloud is sort of off to the lower left corner here. All right. And I think zooming out to the actual galaxy and how the LMC relates to the Milky Way is also a good spot to start with this. So how does the Milky Way relate to the LMC? What we see here, and the LMC has obvious import for a wide variety of studies. Important studies such as the distance ladder, anchoring that for H0 calculations with Cepheids in the LMC. Supernova study is obviously very important because of 1987A as our closest supernova. There's also the closest starbursting galaxy, so there are plenty of massive star-forming regions to look at in the LMC. And for that reason, it's also very important for calibrating dust models. But that's largely not what I'm going to talk about today at all, because what I'm interested in with the LMC is what the LMC tells us for galactic dynamics and what we can possibly learn from that. The talk today is structured in 3 parts here. So the first one, I'll review the LMC in cosmic context. And then in the second part, we'll sort of move on to the LMC's effect on local observations, what we can learn from the LMC locally or in the Milky Way. And then lastly, I'll sort of wrap on a discussion about the role of the LMC in general in galactic dynamics and studying dark matter. So that you're not worried as we go through the talk here about timing, I just want to say that the first part here will be about 50% of the talk. So I'll spend the bulk of the time talking about the LMC in cosmic context in a paper that I wrote recently. And then another 30% on the LMC's effect, and then just the short piece on the studying dark matter. But this is to assuage any concerns about how the timing of the talk is going. All right, so let's come back to this image from Gaia DR2, this great image of the Milky Way itself. And I advertised at the title of this talk is about a new picture for the LMCs and Milky Way interaction. So what's new about this picture? What sort of older picture are we supplanting? And to go back to that, the older picture, to my mind, is actually this one from the 2-mass era. And so now we can convert from the Gaia promotional image of the Milky Way to the 2-mass image of the Milky Way. And you can still see the LMC and the SMC are very prominent in this picture. And so 2-mass was sort of this earlier picture that really was a sea change in our consideration of studies of the LMC. And so what do I mean by that picture? And what did we think of with the LMC at that time? 2-mass doesn't have the same sort of splashy promotional images that Gaia does, but it has some incredible data. This is an image from Nikolaev and Weinberg in the year 2000 here. And you can see, again, I've tilted this so that I've maintained allegiance to the galactic L and B coordinates. So this image is completely tilted on its side. But this is sort of this is the surface brightness image or the source count image from the 2-mass sample. But it's actually more compelling, and a lot of the science was enabled by considering a slightly more refined version of this. And so the 2-mass HR diagram led to being able to split the stars in the LMC very efficiently and give you in particular this one very important set of stars for dynamic studies, which are carbon stars. So the long period variables here that are bright and are a very powerful tool for assessing the dynamics of the LMC. And so in the time after 2000, as this older picture for the Milky Way LMC interaction took shape, these carbon stars were a big part of the workhorse. And one of the things that happened is that Roland van der Merel and collaborators in the time after that started to look at different fields in the LMC using carbon stars to try and gain some dynamical understanding of what's going on in the LMC. And so I've overlaid some of the fields that they were studying for carbon stars and trying to compute a variety of things. And one of the things that they were able to back out is still one of the strongest constraints on the mass enclosed in the for the LMC, and you find that your consistent rotation curve in the LMC is consistent with roughly a 3 × 10⁹ solar mass disk. And of course, in comparison to the Milky Way, this is a little less than a tenth or so of the disk ratio here. But more surprisingly, at least in the context of this study and in the studies in the 2-mass era picture, was that they actually calculated this huge mean motion. So looking at the proper motion of the carbon stars consistently returned this very high mean motion for the Large Magellanic Clouds, which translates into a very large transverse velocity for the LMC and the SMC. This mean motion vector is consistent with first passage, and that's the picture that took shape in the 2-mass era. And then we're still sort of unpacking everything that this means to have a first passage LMC. So coming forward, that's sort of the 2-mass picture developed in the early 2000s based on the workhorse carbon stars. But now we have this treasure trove, obviously, for galactic dynamics and nearby dynamics of in the Gaia satellite. And so if we ask, well, what's different as we're coming forward in this, we can enhance a significant amount of the data. So coming back to this color image from Gaia DR2. You can overlay another beautiful promotional image from Gaia EDR3 that looks at the proper motion vectors in the LMC. And so what this image that I've overlaid here and aligned is showing, if you look very closely, you can see that it's little streaks, and the little streaks in this image are telling you something about the rotation of the LMC. And because we can do this for a continuous field now across the LMC, as opposed to just the spot studies that were enabled in the older picture, we're able to come up with a more cohesive picture for the rotation curve. Of course, what we find is that the results from the van der Merel series were roughly the same And so the EDR3 rotation that came out of these studies are roughly consistent, largely consistent with that earlier picture of that 3 times 10 to the 9 solar mass disk or so. But that's not the whole story, and that's actually not where Gaia in particular excels, and where this Gaia era picture for the LMC Milky Way comes into focus. So where this picture for this modern picture of the LMC Milky Way interaction comes in is using this other piece of information that started to take shape really in the past 5 years or so. So evidence for a massive LMC has begun to take shape. There's a variety of constraints that you can try to refer back to. Is this work that Jorge Penarrubia did, one of my collaborators, in 2016, using the local flow and the motion of the Milky Way and Andromeda in the local Hubble flow to constrain the mass of the LMC. And what Jorge found is evidence for a much more massive LMC. So something closer, much closer to 10 to the 11 solar masses once you consider the dark matter halo. So this is really the sea change in the Gaia era models here. So the models from the 2-mass era considered a slightly lighter Milky Way, in general focused more on the stellar component, didn't have the same sort of evidence for the more massive LMC. And now in this current era, we're able to place stronger constraints on the mass of the LMC and start to explore what these models for that have the LMC being really 1/10 of the total Milky Way mass. So here in this, the ratio of the dark matter mass in the LMC and the Milky Way is again about 1/10 or even above 10%. And we're still unpacking what this means. One thing that is interesting to me, and what I'll sort of spend the rest of the talk unpacking, is this question of where is all of the mass? So if we take that rotation curve that we had from Gaia EDR3, that's again consistent with the 2-mass era picture, and you ask, how do I possibly get up to this 1 times 1 or 2 times 10 to the 11 solar masses in the dark matter halo? Using typical values for typical halo profiles for the dark matter halo, you can see that the LMC is actually extremely extended in this picture. So no matter what halo profile you pick, apart at least cosmologically motivated or roughly cosmologically motivated, you'll see that the mass, in order to get up to this sort of 10 to the 11 that you're expecting, we go out much further than was previously analyzed in models. And what do we find if we model this mass is really the question that I'm going to start asking. So the new models for the interaction are going to explore this higher mass, but also this mass distribution, and try and disentangle what's actually happening in the LMC and the Milky Way interaction. And that's what I really mean when I talk about a new picture. Just to give you some orientation, because I actually forgot to mention it earlier, the solar radius here, the LMC's center, is about 50 kpc from the sun right now. And so what you can see is that actually in these extended mass models, or in this heavier mass model for the LMC, that the sun is well inside of what you might consider for the LMC's dark matter halo. And that will have implications that we'll sort of unpack during the third piece of the talk. Okay. So again, coming back to this Gaia DR2 image and starting to build these models for the more massive LMC, the question that I want to answer or start asking in the first part of the talk here is, how has the LMC shaped the present day sky? The LMC has streaked across the sky in the past roughly gigayear or so, if you put together models. The trajectory is not exactly set. So while I'm giving you a suggestion for the trajectory of the LMC across the sky here, this is not by any means settled, and we don't know if this is going to be the final trajectory, but it's largely consistent between different models, as starting on the left hand side, so starting at high L here and streaking to its current day position. And of course, the SMC in this paradigm also falls in with the LMC. Okay, so again, coming back to this question, how has the LMC shaped the present day sky in this more massive paradigm for the LMC Milky Way interaction? And what do we know? What can we use to try and validate these models? One thing that's been fairly consistent across a variety of modelers in this modern LMC picture, and this is not just my work, but also some fantastic work done by Nico Garrido Camargo, is that there's a clean prediction for the LMC creating a self-consistent response in the Milky Way. So as the LMC falls in, you sort of stir up the Milky Way halo and create this structure where you have an overdensity along the track of the LMC, along the trajectory, and then you also have this companion overdensity in the northern sky as well. This is actually a very powerful tool that we can try and use to check our understanding of the paradigm and the massive model for the Milky Way and LMC. And this is the first piece of evidence that'll offer you that we're getting something right about the models, because in 2021, this was probably detected in K-Giants in this Nature paper from Charlie Conroy's group that was informed by Nico's models that were developed. And then so I started thinking about what we could do in this as well and try and find other means to validate this. One thing, again, of course, this is largely just in density. And so I started to think about whether we could enhance these models or find any more predictions to try and make from these models. And that led me to the Gaia DR2 R Lyra sample, which is really a treasure trove in terms of giving you a sample of distant stars in the Milky Way. And you can see in this image that there are actually many features. If you take the Gaia DR2 R Lyra, and I'm personally really looking forward to the DR3 sample of R Lyra stars, you can see many features in here. So you've got the Sagittarius dwarf galaxy here, very, very obvious in R Lyra stars. But you've also got various globular clusters around, as well as some dwarf galaxies like Carina, for example, here. But there's no obvious overdensity like we saw in the Charlie Conroy's picture that was detected in K-Giants, and so that's a little bit of an interesting feature. And so I started to think about what else could we look at in these models. And there's something that's very obvious in the models, and that's actually the extended distribution of the LMC. So if I gave us sort of dark matter eyes or a dark matter telescope, and we were able to look at what the structure of the LMC looked like in these models, you see that there's a very extended LMC, and I've chopped out the central region here because the dark matter density is obviously incredibly high if you're centered on the LMC and the SMC. But if you look at sort of the lower contrast sort of extended dark matter halo, you see both some trailing material here, but also a very prominent leading arm for the LMC here. And this motivated a question that I asked in this paper that I wrote with Jorge and Ella last year, or it's coming out this year. Instead of the publication date will be this year. And this is a really simple question of, is there a stellar halo that we can detect for the LMC? And what is that actually telling us about these models and this massive paradigm, and how the LMC fits sort of in the hierarchical assembly paradigm? Now, this is an interesting question, of course, to ask for the LMC, and we're not the only people that have asked the question of how the LMC fits in a hierarchical assembly paradigm. People have noted before, of course, that there are no real obvious halo population of globular clusters from the LMC. There are disk globular clusters, but nothing that appears really, really halo-like in the LMC, which is, of course, interesting in the hierarchical accretion. But there is evidence for Magellanic dwarfs, and we'll use some of these as signposts for whether there could be an extended stellar halo. So again, as we move on, the emphasis here is that I'm asking the question, is there a stellar halo for the LMC that would be a tracer of this massive extended dark matter halo that we expect, given the high mass of the LMC, and also and the hierarchical accretion or the hierarchical assembly paradigm? All right, let's zoom in again. We're coming back. This RLIRA sample is going to be the workhorse sample for this, for the results from this piece of the talk. And so if you zoom into the LMC SMC region and you look at the RLIRA sample, we can do two things here, which is where I've given you all of the RLIRAs in these sort of in the gray points. The larger gray points are the RLIRA stars that are at greater than 25 kpc. So sort of where you might start to think that you'd pick up LMC stars. What I want to emphasize is that just looking at density features is not actually sufficient in this. You can be fairly, you can be strongly biased by just inspecting density features in here. And what you really want to do is use the velocity features. And that's what I've done in the rest of this. We looked at LMC-like velocities, proper motions in the RLIRA stars that have the 5D sample that are consistent with this. And you can see that there is actually a very extended population of RLIRA stars around the LMC. And I want to emphasize that these curves here, and again, I've squared galactic space, so the circles of constant distance from the LMC are deformed in this space. You go out 15 degrees and then 20 degrees and all the way up to 25 degrees and even some stars beyond the 25 degree. And all of these regions, I didn't mention this, but all of these regions that are just white, where we don't have RLIRA detections, are really blanked out because of a fairly conservative extinction cut. So everywhere that we aren't hampered by extinction, we see this sample of we see evidence for RLIRAs that are consistent with the LMC. And so the question then is the distribution of stars here consistent with a halo? It's not entirely clear, but one piece of evidence that is very clearly true is that several of these stars are outside of features that are thought to be inside the LMC halo. In particular, I want to lean on Carina 2 and Carina 3, which are laying on top of each other here and are well inside of some of the RLIRA stars that you detect at much larger distances. So I would argue, and I do argue, that this is consistent with some sort of stellar halo. There have not been disk features detected out to this distance, although disk features have been detected out to 20-ish degrees in the LMC. So how did we do this? What we did is we used the n-body models, and n-body models, I think, are still sort of some of the crucial tools that we need to develop as we're disentangling this paradigm for the LMC and Milky Way interaction. And what you see is that if you ask where the mock LMC, particles are actually located, what you can see is that you can draw a direct line from the LMC or a trajectory running into the northern hemisphere, all the way into the northern hemisphere from these stars. And I'm using two things here. I'm using the LMC and then this stellar cluster, Price-Whelan 1, that's thought to be in the leading arm of the LMC as anchor points. And so if you just draw a naive trajectory between those two and ask, you see that at least in the stars, in the n-body model, that it roughly traces the trajectory that you expect here. And so to create a sort of search space for these stars, we defined these two boxes for LMC stars to try and create a high purity sample. I mean, you can see why. It's because when you look at the mock Milky Way, and obviously in the end, what you're detecting is the superposition of the mock Milky Way and the mock LMC, you end up with a very high purity sample if this is the region that you consider. It's relatively low completeness, to be fair, because you're missing, particularly in the galactic latitude velocity, you're missing a wide bulk of the LMC stars. But again, you have a high purity sample. We estimate about 1% contamination if you use this box. Okay, so I've hidden the data side. So what do we actually see when we look at the data? Well, you see the superposition of the two here clearly. If you added these two up, it looks sort of like the data. I think we still have to improve the models, but we're headed in the right direction. The LMC is in the correct place. You can see these stars that I showed you on the previous slide in the southern hemisphere that are extended out to 25 or even 30 degrees from the LMC. And then you see this other thing that we talk about, that there are actually stars in the northern hemisphere, even in this leading arm, that if you remember the picture that I had for the LMC's extended distribution, that we do actually predict some stars in the northern hemisphere as well. Now, there's one glaring thing here, which is obviously that we're missing line of sight velocity data for all of these our Lyra stars, and this will be one of the things that helps to confirm or refute these. And it should be very straightforward, because the line of sight velocities for the LMC are significantly higher than the Milky Way line of sight in this region of the sky. And just to emphasize that this, again, would not be possible without n-body simulations that are looking at the time-dependent interaction of the Milky Way and the LMC. All right, what do those northern stars look like? To give you an anchor here again, so Pryce-Wheelan 1 thought to be in the leading arm of the LMC, coincident with all of the Magellanic stream gas that you observe. That's been observed actually in the northern hemisphere. You can see these stars are in the northern hemisphere. They are very tentative, but they're sort of consistent. They're very consistent, rather, with the velocities that you expect. And this sort of gets you into the realm of the stellar halos that you might expect. So I think we have detected an extended stellar halo for the LMC, but we still need to do quite a bit of work. So just to put this in cosmic context, of course, nearby galaxies largely show stellar halos that have 1%-ish of the stellar mass of their host galaxy. The Milky Way is the anomalous one, actually, in this plot. Down here, it's sort of only 1% of the stellar mass. If you ask what the ratio of the stellar halo to the stellar disk mass is in the Milky Way. And our closest companion galaxy, M31, closest massive galaxy, rather, I should say, M31 is up here at sort of more than a tenth of the mass. You have a very high mass stellar halo. What you've probably noticed when looking at that slide is that I was very focused on Milky Way mass galaxies, and pushing down to this LMC region is a real challenge. And right now, I think that the best data that we have is sort of one data point down here, which is NGC 3077. And this happens to be very well studied because it's part of the M81 group. And you can see sort of in this low, this high contrast, rather, image, that NGC 3077 has sort of diffuse light around it. Again, this is a very massive, calculated to be a very massive stellar halo. But we can sort of debate whether we're convinced by that or not. I tend to be an optimist in all of this, though, and even if we pessimistically assume a 1% stellar halo, I still think there could be 10 to the 7 solar masses of material. So thinking about that, 3 times 10 to the 9 solar masses in the LMC disk. This is probably sort of roughly what you might expect if you're pessimistically assuming 1% in the hierarchical accretion paradigm. Okay, so I'm going to come back to this image for the LMC. This is a clean prediction that we had from the models that we constructed, and then asking that simple question: is there a stellar halo around the LMC? And then, to me, the key question is, if there isn't, what is this telling us about hierarchical assembly and how the LMC fits in the CDM paradigm? All right, so we're at the conclusion of part 1 here. And I have some optimistic takeaways here. I think that we seem to be getting the LMC Milky Way interaction largely correct. So the things that we've been able to check, we found evidence for this large scale deformation of the Milky Way, suggesting that we're sort of in the ballpark for the mass of the LMC at this 10% mass, this new picture. But then also, sort of interestingly, that the LMC might be a little bit strange in the hierarchical assembly paradigm if we can't lock down more of this stellar halo or find sort of conclusive evidence for an extended stellar halo. And as we're pivoting to the second piece of the talk here, the question that I want to ask is, can we use the velocity information that we have available in a little bit more detail? So I've been kind of hamstrung in the first part of the talk by talking about a 5D sample where we have the Lyrae stars that just have that are missing line of sight velocities, and I emphasized how much we need line of sight velocities. But that's not the only stellar sample that we can use. We can actually try to get 6D samples and look at what their implications are. All right, so coming back to Gaia's all-sky view, one of the advantages, of course, of the Lyraes is that we had this all-sky image. If you're restricting yourself to a 6D sample, you are beholden to sort of what's accessible in SDSS if you want a sort of large sample. Obviously, there are pockets of the sky that have been studied extensively, and we'll talk about some of those in a minute. But I'm really asking how we can try and construct an unbiased view of the sky in general. Okay, so given that SDSS coverage, what we have, our best samples are these K giants and blue horizontal branch stars, where they give you the highest density of tracers. Our Lyraes are obviously far and away the highest density of tracers here and extend out to very large distances. But again, that key problem where they're missing the 6-dimensional data. K giants and blue horizontal branch have the 6-dimensional data. They start to fade out sort of around this 100 kpc, where you might hope to go a little bit further. Satellites of the Milky Way, satellite galaxies of the Milky Way go significantly further, but of course, we're talking very small number of statistics for those. And globular clusters, which have 6D data, again, are even fewer number density than once you get out of the center of the Milky Way than the satellites, and they start to fade out at a little bit lower distances. Okay, so the two samples that we're going to focus on mainly on here, well, 3 samples, we're going to focus on the K giants, the blue horizontal branch, and then as sort of an extension, the satellite galaxies that have 6-dimensional samples. And again, coming back to this image of the all sky, if you look at the data that we actually have in the K giants and the blue horizontal branch stars and the satellites, what you actually start to see is this all sky image or this all sky signal that's emerged of the LMC. And we talk about this in this paper that Jorge and I wrote in 2021. That's this all sky signal where it appears that the disk of the Milky Way is traveling towards this one particular region on the sky. So you have this all sky dipole signal that is imprinted on these samples of distant stars. So what does that actually look like? It looks like this. It looks like this, which is an all sky sample. It looks like there's some enhanced velocities in this one direction in line of sight velocity here, and a decrement on the opposite side of the sky because you're looking at a dipole here, and this projects into both VL and VB as well. And the thing that you should be picturing here is that this is very similar to if you're driving in a car in the rain. You know that the raindrops are falling straight down, but if you're driving in the car, it looks like the raindrops are coming sort of right at you. And that's the signal that we were able to detect here. You start to see, okay, the stars in this region of the sky, or the tracers, because it's also in the satellite galaxies in this region of the sky, they appear to uniformly be coming towards you. On the other side of the sky, they're uniformly receding from you with this sort of travel velocity. And I want to emphasize that you actually would need the 6-dimensional tracers to do this. One reason that we can't do this with the Lyraes is because you have to be able to break the degeneracy with rotation in the halo. This is something that we considered a lot when we were writing this paper. All right, so to give you a schematic picture for what's actually happening, again, I said all of this in words, but sometimes pictures worth 1,000 words and better than my descriptions. So what's actually happening, and this will replay in a second, is that as the LMC falls in, you're starting to pull the stellar disk of the Milky Way away from its original center. So the vectors here in this animation are the velocity of the individual components at that exact time. And what you can see, obviously toy schematic, don't take any of this exactly to scale or the time suggestions. But what you can see is that the LMC is actively displacing the stellar disk of the Milky Way away from the barycenter. And it's doing this with a particular velocity. And that's the all-sky signal that we measured. This sort of hangs together with a fairly rudimentary picture asking how fast the displacement or how much displacement of the Milky Way disk there actually is. The magnitude of the instantaneous velocity here is similar actually to the velocity of the LMC, which is 300-ish kilometers a second, and the ratio of the Milky Way and the LMC, which is roughly 10%. So we come out with a very back of the envelope calculation for 30 kilometers a second, which is roughly what we actually observe in the stellar samples. So the best estimate that we have here is actually combining all of the samples. And so you end up with something very similar to 30 kilometers a second. And what that's telling you is that's the velocity with which the Milky Way disk is currently traveling with respect to its former, to the location at the barycenter of the Milky Way halo. So you have this strong deformation in the Milky Way. I will also point out, of course, that this direction, this may have triggered something in the back of your mind from the earlier part of the talk, that this direction of travel is coincident with the all-sky signal that you expect in the Milky Way over density. And this is one of the reasons that I think we need to do significantly more work to understand the all-sky signal in the Milky Way, because if you overlay the direction, you're sort of traveling exactly towards where you expect that overdensity to be taking place. And it's fairly straightforward to imagine that if you're traveling in a direction that you'll start to see some overdensities in that area as well. And this, to me, doesn't exclude the data. It doesn't exclude this all-sky signal. This is something that we've conclusively or that we've predicted very strongly in models, but it does highlight the need for velocity data. And that then motivates this question: what else can we look at? And depending upon your observational bend, and if you're interested in the stellar content of the Milky Way, you may already be yelling at the presentation that I should be considering stellar streams. And this is exactly what we've done. So stellar streams have 6-dimensional information, but in contrast to the SDSS style sample that I was talking about that has sort of wider grasp and coverage, you have specific orbits that you're tracing in the Milky Way. People have shown, collaborators, Dennis Urkel in particular, and his collaborators have shown that several streams, and I'm going to focus on the Orphan Cheneb OC stream here, show huge effects from the introduction of the LMC. And this is an image from Dennis's 2019 paper that shows that if you neglect to include the LMC, or you include the LMC at its sort of 2-mass era picture mass, that you can't possibly fit the stellar stream that you see, the whole stellar stream that you see for Orphan Cheneb. It's only when you start to include this much higher mass, so around that 1 × 10⁻11 that I was talking about before, that you start to get much closer to being able to fit the actual data here in the stream. Okay, so what's actually going on here, and how can we sort of think about the next generation of models? One thing that I want to emphasize when you run these n-body models is that these live n-body models is that you start to see significant deformation. So running through time here, what you start to see is that the LMC is getting extended along its orbit, but the Milky Way is also deforming. You can see at the end of this that these contours are very strongly non-circular anymore if you're just considering the Milky Way or the LMC in these images. And this is something that a fantastic student, Sophia Lilla Engen, has been studying. And Sophia's at the University of Surrey right now. She'll be on the job market next year. And she's been doing a great job of exploring the implications of these deformations for what the impact on stream observables is. So taking Dennis's earlier work, where the LMC and the Milky Way are represented as these extended monopoles, so they're spherically symmetric, Sophia's taking it to the next level and asking whether we can detect any of these deformations that are so clearly predicted by the n-body models. And just to spoil this paper that you'll see in the next month or two, a live model for the Milky Way and LMC interaction makes a measurable difference on these stellar streams, and in particular on the Orphan-Chenabb stream, which is the one that we're considering here. Sophia's measured this in a variety of ways. What you see is that at the quality of data, essentially, that we're getting for stellar streams now, you have average uncertainties in the position of the stream track that are very small, 10/10ths of a degree. But what you see as you start to include successively more deformations or look at different components of the deformation in the LMC and the Milky Way is that you have a range of effects here. So if you don't consider the deformation of the galaxies, then you will strongly bias your results for stellar streams. And so this to us is a key, really suggests that you need to consider deformations and need to consider some of these higher order things if you're trying to do some real stellar stream modeling in the Milky Way. As a brief aside, I won't talk about this because it's an entire other talk in the technical work that I've been focusing on. But the way that this is accomplished is through basis function expansions. You might have heard about this before if you read Nico Garavito Camargo's paper or any of the work that I've done, where we're efficiently describing the potential and the density using basis functions. And that's what you saw in that video that Sophia put together for the Milky Way LMC interaction. And just to say that with basis functions, you can do some very simple characterizations of what's going on. And Sophia's found that the Milky Way in particular is dominated by the dipole, so stretching of the Milky Way towards the LMC. The LMC, conversely, is dominated by the quadrupole, where you're gaining triaxiality in the tidal field. And that's what you're seeing here for example, as the LMC gets more extended, as you start to include more and more terms. I'm happy to answer any questions about this, but that's just, again, that's a whole other talk. Okay. We're at the stopping point for part number 2 here. I want to give you a couple summaries that I looked at in that section. And the first one is talking about that we need to consider the LMC when measuring Milky Way properties. So I showed that the LMC is actively displacing the Milky Way. If you are to try and measure things about the Milky Way, you're going to have to take into account this all sky velocity signal that the LMC is imprinting on the Milky Way. Then I talked about the impact of the LMC on stellar streams. The LMC is most likely, I wrote likely deforming, but I will say it is definitely deforming most of the streams, and how concerned you should be depends on the precision of your measurements. So if we're trying to do precise measurements for the potential of the Milky Way or the structure of the Milky Way, these are effects that we'll have to consider with successively more complicated models. And for better, for worse, this suggests that a strong argument for needing time-dependent models of all LMC Milky Way components. And that's one piece of the technical research that I'm working on. For the end of the talk here, I'm actually going to switch gears a tiny bit and consider, again, what other kind of predictions that we can make. So I started talking about this picture for the Milky Way LMC interaction paradigm. I'm very interested in always trying to come up with different ways to validate these. One thing that I talked about was how in the picture that we had before, or this extended mass model for the LMC, that the LMC stellar halo should overlap with the solar neighborhood. And that's something that I looked at with a student in Edinburgh who wrote a fantastic paper. This is Caitlin Donaldson's work that was just accepted earlier this week. So a big congratulations to Caitlin, who's wrapping up her MPhys at Edinburgh right now. It'll be starting graduate school next year. And so Caitlin looked at this question. So we think that if we think that there really is an extended dark matter halo for the LMC, then there should actually be some dark matter at the location of Earth. some LMC dark matter, rather. Of course, there's dark matter in the Milky Way. And so Caitlin looked at the dark matter particle velocities, and this is really motivated by direct detection experiments. So on Earth, there are these terrestrial direct detection experiments that are trying to find the WIMP scenario for dark matter that are triggered based on the velocity of particles that are passing through Earth, dark matter particles. And what you find is that even if you consider a static model, so in this first model, you take the LMC and you put it at its present day location, you have some sort of stellar halo, or you have some sort of dark matter halo around the LMC, and you look at just what the velocity is. And because the LMC is coming in so quickly, even in this static model, the high velocities are very strongly affected by the presence of the LMC. Of course, I don't want to overstate what's happening here. The LMC is, because of its mass ratio and its distance, is still dwarfed by the contribution for the Milky Way dark matter. You can see in this model that we put together, just by means of another validation, the dark matter density at the solar location is roughly in line with what people predict, between 0.3 and 0.4 GeV per centimeter cubed. But the LMC's dark matter density at the solar location is 1,000th-ish of that, or a couple 10,000ths of that. But that's not where the story ends, because if you actually ask what happens in the N-body models where the LMC is deforming in the presence of the LMC, what you see is that the velocity of the LMC particles gets an even stronger boost. So even though you might have this strongly reduced dark matter density at the solar location from the LMC, these particles dominate the high speed particles in the solar neighborhood. So this is even more extreme. So now you can see the LMC distribution here at extremely high velocities, and the Milky Way distribution in black here is dwarfed by it. So if you have a direct detection experiment that's sensitive to higher mass particles, or higher velocity particles rather, there's a good chance that if you were only sensitive to greater than 750 kilometers a second, for instance, that the only particles you'll be actually detecting are dark matter particles from the LMC. But I don't want to, it's not the only thing that's being affected here, of course. If you take off the LMC and we ask what's happening in the Milky Way particles are still experiencing a velocity boost. And if you zoom in on this, you can see that it's a small tens of kilometers a second velocity effect, shifting the distribution from the static model, which is dashed here, to the live model, which is solid. And this is reflex motion at work again. So yet again, the motion of the disk moving changes the velocity structure that you see in dark matter particles. This might also be an effect that you want to consider for halo stars, local halo stars near the sun, that instead of just modeling a static distribution for the Milky Way halo, you will also need to consider this reflex motion boost if you're trying to just keep accounting for what the velocity distribution of halo stars looks like. And just by means of conclusion on this work, one thing that you find is that Milky Way dark matter particle origin is very localized. So the direction that the particles are coming from, because of solar motion around the galactic center, is very localized. And if you were sensitive to the direction that these particles were coming from, or halo stars are coming from, then you'll find that they come from this direction. The LMC is actually inconsistent with that. So if you ask where LMC particles are coming from, it's a similar direction, but they are distinct. And I've given you this all sky image, but there's something like 25 degrees separated from each other. So if you have a population of Milky Way dark matter particles and a population of LMC particles, dark matter particles, you'll be able to distinguish between these two. All right, to conclude for part 3 here, if this is a big if, the LMC contributes to the dark matter distribution at the solar location, those will be the highest velocity dark matter particles. Similarly for halo stars. But the Milky Way dark matter particles are also going to experience a boost And one of the powerful ways that we can try and distinguish between these is to have some sense of the directionality and have a population where you compute as a function of velocity what direction the particles are coming from. Looking ahead, just what is the prospect for future models of the LMC and Milky Way? To model the Milky Way, we also need good models for the LMC. So it's not sufficient to just consider the Milky Way anymore. We also have to consider the LMC, and how detailed of an LMC model you should be designing depends on what types of questions you're going to ask. Observationally, the thing that would help us the most would be to get 6-dimensional samples. So get those line of sight velocities that are at distance. And so for an observationally minded crowd, this would be extremely helpful for people that are trying to model this. And I think that there are some very low-hanging fruit, things that could be studied with a 6-dimensional sample across wider swaths of the sky, of course, at distance. So I recognize that this is hard because you're talking about faint and specialized stars. And then on the technical side, we also need to develop some of the technology for disequilibrium dynamics. So the Milky Way and the LMC are obviously not in equilibrium right now. The LMC is still falling in and affecting the Milky Way. And that's some of what I'm working on with basis function expansions with a variety of people. All right, so the summary for the whole talk. Thank you for listening. We do seem to be getting the LMC and Milky Way interaction largely correct. So the things that we've been able to think to check have suggested that we're doing pretty well with this. But the LMC still has several puzzles, principally the disequilibrium structures. And you can see obviously in the DR2 image here, I emphasize that there's disequilibrium in the disk, and we haven't studied that at all. I've been looking at the extended distribution. And then the pre-infall LMC structure. What did the dark matter halo of the LMC look like before it came in? And obviously, I haven't mentioned anything about the SMC, and I fully expect to answer some questions about that. And then also, interestingly, the LMC has information for us to test dark matter models, and we want to try and figure out how to ask the right questions for things even beyond direct detection. So with that, I'll stop. And thank you very much for listening, and I'm happy to take any questions that you might have.
Thank you very much, Mike, for this really, really nice talk. I'm sure that a lot of people are joining me to applaud you for this really nice presentation. So now if people have some question, please raise your hand and mute yourself. So is there any question for Mike? Martin? Yeah, we can't hear you.
Now you can hear me?
Yes, yes. Thank you.
Yes, so sorry. I would like to...
It's kept again. Maybe you can write it in the chat otherwise.
No.
It's good now.
It's now, no?
Yes.
Sorry.
It's cut again. So maybe, okay, so let's write your question in the chat and I will ask it directly to Mike. Okay, thanks. So is there any other question? Almudena, I see that you have unmuted yourself. So do you have any question?
Yes, I hope to have more luck than Martin. Very nice talk. Thank you very much. I have a question related to what, I mean, Andromeda is also coming to the Milky Way. You are saying that the Large Magellanic Clouds is also coming to us. I suppose that the Small Magellanic Clouds maybe too. Why is that? Is the potential of our galaxy? So the Andromeda is very heavy as us, so it's not a bit suspicious. Sorry. In all of them, we are moving towards the grand attractor as well. So. Okay.
Yes. So, yeah. I think. Yes. So the local group is very complicated to model, and I think that's certainly somewhere that I'd like to go next. I think the orbit of the LMC obviously is very interesting, right? So it's or the infall velocity of the LMC is very interesting. It's coming in very quickly. And one thing that we're not sure if you run these models forward is if the LMC is actually bound to the Milky Way at all. So it might be, if you run this forward, that the LMC is just an interloper that just happens to be passing by. For Andromeda, I think we're just coincidentally seeing the time period in history where after the Big Bang, obviously, we started going off in different directions, and just gradually we're starting to come together. I think there's a good question in local group dynamics whether the Milky Way is attracting Andromeda, or whether Andromeda is the dominant attractor relative to the Milky Way. I don't know yet. I think if you stay tuned, though, in about a year, maybe, I'm starting to tackle the Andromeda question, because I'm really interested in this idea of, like, how does the whole dynamics of the local group work? Does that answer your question?
Yeah, I was trying to understand what is the explanation of, if supposing that the Large Magellanic Clouds indeed come to us, why is that? Andromeda as well, why is that? They could be a relative motion, okay? Maybe, who knows what is moving to who?
Yes.
But
one other piece of evidence is that, and I didn't talk about this, but people have studied this ad nauseum. So the satellites, of course, of the Milky Way appear to be in a vast planar polar structure, right? So there's the satellites of the Milky Way largely follow one particular plane, and the LMC is also in that plane. What I personally find to be the most convincing argument for that is that they just all happen to be following the same intergalactic filament. And so if everything in the local group is actually dominated by this huge filament that's feeding us the LMC, for instance, and it's also feeding us Andromeda, because you're right, they are coming from the same direction. I think that there could be some even larger scale dynamics at play, but we're going to have to work on that.
Okay, nice. You should compare with cosmological simulations. Maybe you are in this web.
Yes, I think that's right. But of course, the LMC is a low probability, appears to be low probability in LCDM. So getting simulations that model this, cosmological simulations that model this, is a big challenge. But thank you. Yeah, it's a great suggestion.
So the question of Martin was about the galactic warp. So it is, have you investigated the effect of the interaction of the LMC with the Milky Way with a new mass estimation?
Yes, thank you, Martin. This is a fun question. And you're probably thinking of the fact that in the 2-mass era picture, the galactic warp was studied as something that was caused by the LMC. But of course, in the 2-mass era picture, the LMC was 1/10 of the mass that we think it is now. So, like I said before, and Dennis Urkel's work showed that earlier mass that was sort of 10 to the 10-ish was shown actually in some work by Martin Weinberg that you could trigger the warp of the Milky Way in H1. The modern picture is slightly more complicated, because at the time that picture was developed, the interaction with Sagittarius wasn't fully fleshed out. So now with the Sagittarius interaction, and I didn't talk about Sagittarius at all in this talk, other than to show you it in our Lyras. The interaction with Sagittarius is also a compelling possible cause for the warp. But I will say, and this is not work that we've published yet, but if you do look at the vertical structure for the LMC, for the Milky Way induced by the LMC, you do get a strong warp. What you don't see is the same sort of asymmetric warp that you see in the Milky Way. So the Milky Way's H1 sort of appears to sort of look like an integral sign, where it's positive on one side and negative on the other. What you see in this picture for the LMC is something that's a little bit more like a bowl. So instead of the integral sign, what you actually see is that the outskirts of the Milky Way are largely being pulled up. So I don't know that the LMC in this paradigm is the only answer to cause the warp, but I think that if you wanted to design a warp model, for the Milky Way, you'll have to consider both the LMC and the effects of Sagittarius, which makes it a very complicated problem right now, unfortunately.
Good question indeed. So is there any other question for Mike? No, sir. So I have one. So at some point you show the distribution of density of aerial iris detected with Gaia DR2, and you didn't find the overdensity of K giants that detect Charlie Conroy. Do you have a, well, yeah, so I would like to get your opinion about that. So why?
Yeah, I invited this question, right? And I should have been more careful. So yeah, I don't know. I think, and I mentioned one really key thing, which is that Gaia DR3 is going to update this sample strongly with the RL iris. And so I think right now I'm actually going to punt the question and say, come back to me after we make this map for DR3. And if you still don't see this overdensities in RL iris and DR3, where you're not as worried about scanning law patterns, because what you can, if you look at the RL iris in this, you can still see obvious scanning patterns if you look on discrete levels. But DR3 should wash most of that out. If we still don't see the overdensity, then I think we're going to have to look more carefully at the K giant sample and try and figure out if there was something that we missed in that. So again, I'm going to come back to the K giants here. So this is density contrast. So there's obviously an overdensity in this region. Again, one of the things that I said was that this is coincident with the location of the reflex motion. So if you're not considering reflex motion, we have to be a little careful here about possibly overinterpreting this, and especially overinterpreting the south versus north. The other possible way out is that it could be that K giants and RL iris have different radial distributions for some reason. So this effect is radius dependent, or the deformation of the Milky Way is radius dependent. So if for some reason the RL iris, which are largely thought to be this very old sample, if they follow some sort of different distribution compared to K giants, then you might be able to sort of give yourself enough wiggle room to not see these. But I think this is one of the big questions, is sort of, if you think that this detection is real, why don't we also see it in RL iris? There's still enough uncertainty that I'm not super worried. But a year from now, if we still can't figure this out, then I will actually be a little bit more worried about the detection in the first place.
And I have a very quick another second question, which is about the detection of the dipole positions. So it's really hard with non-homogeneous data. So how certain are you of this angular detection on that you are just picking the good position? Like, what is the uncertainties due to the method? Not only on the data, but the data of the dipole that you detect. Yes.
So so this what I'm showing here actually is sort of our uncertainties, right? So I don't know if you think this is small or large, right? So it's obviously a vast area, a fairly vast area in the sky. So we have a most probable location. You can see that there's some tension between the different samples, obviously here. So there, and some of this, okay, I think there were two questions there. So I'm confident in what we have here. And even though we don't have uniform sampling, so I showed, sorry, I can get back to that slide too. So even though I showed that we don't have uniform sampling across the sky, we actually worked really hard to validate the method, and you can go in the paper and there's sort of this gory detail, right, for everything that we fit in the sample. And so you can see that largely there's no covariance in all of the things that we studied. The ones that you're concerned with are the dipole parameters, or the location of the dipole parameters here. fairly consistent. We're not super worried about that, but there are some degeneracies. You can redo this with EDR3, and if you redo this sample, because this was done with DR2, if you redo this with EDR3, you get roughly the same thing, but there is some subtlety, and I'll just, well, you know, since this is being recorded, I'll be careful, but this is stuff that we haven't published yet, which is that if you try to slice this up in distance, you actually get a different response. So you have some imprinting of the trajectory of the LMC as it falls in on this. And so I'm going to, you know, I'll politely redact everything else on here, but we're seeing evidence that we might be able to get a better constraint of the trajectory of the LMC and the mass of the LMC based on slicing this up in distance, and that gives you a little bit more certainty.
Amazing. Really looking forward to this. All right. So thank you very much. So if there is no other question, let's thanks Mike for his really kindness to have presented his work, and see you all next week for 2 other seminars. So thank you really much for